Good morning. Hope everyone got their coffee. So wonderful to have you all here. Anyone who doesn't know me, my name is Risa Wechsler, and I'm the director of this new Center for Decoding the Universe, which has been a fantastic partnership that we started earlier this year with Stanford Data Science. So really thrilled to have you all here today and tomorrow, and I'm going to say a few more words about that in a minute, but first I'm going to hand this off to Guido Imbens, who's the director of Stanford Data Science. Thank you.
Thanks, Risa. So my name is Guido Imbens. I'm director of Stanford Data Science. I've actually only been director here for 2 months or so, so I'm all very new to this. But welcome to the conference organized today by the Center for Decoding the Universe on data-driven discovery in the Rubin era. This building actually has only been open a couple of months ago, and it's been a spectacular success in terms of the engagement of the students. If you've walked around this building, you see it's just incredibly nice in terms of the way it allows the students to come in and be engaged with the faculty. And of course, this particular room, the conference center, is an incredibly nice room for having these events. I think the only problem with this room is standing here at the stage. It's a little distracting to see this incredible view outside, but it's less of a problem for you guys. I want to make a couple of brief comments about Stanford Data Science. I'm actually an econometrician by training, so you may wonder what I'm doing here today. But Stanford Data Science brings together faculty and students from all over the university who are interested in or using data science methods. And the vision is that data science methods that are developed in some areas can be very useful in other disciplines. And therefore bringing together methodologists from all over the university with researchers with expertise in substantive areas can be very useful for advancing these substantive areas. And this is something that's been important to me in my own career, where I've greatly benefited with from working with researchers, not just in economics, but also in statistics, biomedical sciences, environmental sciences, and other areas. But back to the Stanford Data Science, the three main activities that we engage in to fulfill this mission. First, there's a focus on creating a high-quality computing infrastructure. Since last August, we have a cluster of CPUs, Marlow, that has enabled computationally intensive research of the type that hadn't been feasible here at Stanford previously. And in fact, Risa Wechsler and Susan Clark have been among the first active users of this cluster. Second, Stanford Data Science hires faculty. We do not do so on our own, but jointly with other departments, with those faculty spending time both in their own departments and in this new data science building. So far, we've hired 4 new faculty. Brian Trippi joined with statistics. Brian He joined with chemical engineering. Laura Williams joined with psychology, and Ludwig Schmidt joined with computer science. The third part of what Stanford Data Science does is organize the research centers, where we currently have 5, with 2 more on the way. These are faculty-led research centers that bring together faculty and students from Stanford and other research organizations in areas of common interest. These centers include the Center for Decoding the Universe that Risa Wechsler and Susan Clark lead, the Center for Reproducible Science, the Center for Sustainability and Data Science, the Center for Data Science Research for Biomedical and Healthcare Innovations, and the Stanford Causal Science Center. These centers bring together researchers from Stanford and also organize activities involving researchers from other universities. The conference today and tomorrow is the annual conference for the Center for Decoding the Universe, and I'm very excited to see participation from researchers from all over the world here, and I'm looking forward to a very interesting set of presentations. Let me end by thanking the staff from Stanford Data Science for all the work they've done in putting together this conference, and let me wish you a great 2 days here at Stanford. Thanks.
All right, thank you so much. So I'm just going to briefly say a few words about our center. So as Guido mentioned, we are the 5th research center that's part of Stanford Data Science, and I think there's more coming. What's really exciting about this has been this real partnership, between KIPAC and Stanford Data Science, and we really have thought right from the beginning about how do we build partnerships across the university and with methodologists, outside of astrophysics. So really our goal is to build interdisciplinary collaborations that leverage complex data to infer how the universe works. And we are starting with astrophysics as a core thing, but I take the word universe to be very expansive and inclusive. And so probably most of you, even if you aren't astrophysicists, are interested in problems that are part of the universe. So we actually have already had 2 quarterly forums, which have been wonderful half-day meetings where we've actually brought people together from many different disciplines that have methodologies that have relevance in astrophysics. We have a bi-weekly journal club that's been really, really wonderful for getting especially junior people talking to each other across the university and from different parts of the data science and AI ecosystem at Stanford. We've started just in the last 6 months or so to nucleate around some community projects that I expect will be evolving. We've already had some co-supervision of student projects between astrophysicists and computer scientists, and I expect many more. And for those of you who are at Stanford and would like to engage, if you haven't engaged with us actively yet, you are very welcome and happy to talk to you more about what that might look like. So I just want to say really briefly just about some of these community projects, just to give you a flavor of some of the things we're thinking about. So this is a beautiful slide that Dalia Barron here put together, showing how much incredible data we have on nearby galaxies. And so really thinking about how do we encode that multi-scale, multi-wavelength data on galaxies in the nearby universe to really learn new physics. What's happening in the ISM? What are the conditions of star formation and gas cooling and feedback and all of these things that are encoded in these data that have not really been put together. And we think there's really new possibilities for innovative data science and AI techniques in this space. Another really fun project that we've been working on the last few months called Research Bench. There'll be a short talk on this later today, I believe, by Christine Yi, and Joe Suika has been really playing key role here, asking whether AI agents, how well they can do reproducing complex tasks in astrophysics papers. So far, the answer is not very well, but we have a really nice benchmark that anyone can test their favorite model on, and it does much better on easy tasks like counting the number of stars in a data set than it does on much more complex tasks. So that's already been a really great learning experience, including for me, about what the capabilities of these agents are. And then there's been a wonderful project that Tom Abel and many young people have been thinking about. How can we really build sort of realistic 3D physical constructions of all or any astronomical objects? Again, from multispectral data and really thinking about a differentiable forward model. And I think this is a really, really exciting approach to some of this. So that's just to give you a flavor. All the people working on these things are here in the room, and you should please feel free to talk to them about more here. I'm going to pass it off to Susan in a minute, but I just want to say, we really are sort of at the core of this center, really trying to think about how do we build effective collaborations across fields. And I would love to hear from any of you what you think, what's most exciting in that space. What are the ways that astrophysics can drive forward methodologies? Where are the places where we're not thinking hard enough about the methodologies for our science, et cetera? And we're going to hear more from Phil about why we called this in the Rubin era in just a few minutes, but we are in a really, really exciting time in astrophysics that we think is going to be very largely enabled by our collaborations with data science and AI. And so I hope we'll get some excitement about that in the next few days. So thank you.
All right, perfect. And I'm Susan Clark, assistant professor in physics and co-director of our center. And I'm just going to briefly give you the overview of what we're doing here today and tomorrow. So as you know, we've themed this conference around our dawning Rubin era. Phil will tell us much more about what that means in a minute. But we have created 3 sessions for you that we felt incorporated or used some of the exciting data and methodologies that will be very relevant to this new facility that we'll have and all of these wonderful data we'll have with the Rubin Observatory. So we have sessions on time domain data and anomaly detection in all manner of data. We have a session on modern inference frameworks, and in particular, their application to cosmology, although not exclusively. And we have a session tomorrow on galaxies and thinking very broadly about foundation models in lots of different applications. In between, we want you to eat and talk to one another and mingle and try to interact with people from different disciplinary backgrounds, because as you walk around and meet each other, you'll realize that we really represent a great breadth of disciplines within academia and beyond. Tomorrow we'll hear more about the organization of our half-day unconference. Today we will have 2 of our main sessions and a panel discussion in the evening after our reception. At each of the breaks, there will be an opportunity to look at the fabulous posters that many of our attendees have prepared. And I want to just quickly explain to you the anatomy of each of these sessions and the way that we've tried to craft this conference to make it as interactive and discussion-based as possible. So we're going to open each session with 3 invited talks. These are talks where we have asked our speakers to actually talk to one another beforehand, coordinate a little bit, think about the big problems in their field, in their topic, and present to you some of the exciting data, exciting methodologies, and maybe big unanswered problems inherent to their discipline. They'll talk to us, and then we will have discussions with the people at your round table for a half hour after each of those, or after the session of 3 talks. We'll give you a little break to get some coffee and rest your mouths. Well, actually, to talk to each other more. And then we'll come back together for some contributed talks. We have 5 exciting 5-minute talks in each of these sessions, followed by 1-minute talks from anyone who is giving a poster who would like to give a 1-minute talk about their poster presentation. And then we will discuss as a larger group all together. So this is what's happening within each of these sessions that I just mentioned. You can use this QR code to get a map of the posters that are out there, and that might help you plan where you'd like to route yourself during your breaks. But I hope you'll take advantage of this time to talk to each other, to ask big questions, and to really get inspired about what we're going to do in the era of Rubin that Phil will now tell us about. Thanks.
All right, morning everybody. Welcome everybody, great to see you. My name is Phil Marshall, I'm a senior scientist at SLAC and also Deputy Director of Operations for Rubin Observatory. So in most of my time I get to think about how to make this wonderful new facility work, but in a small fraction of my time I get to think about science to do with the data that Rubin will produce. So here is the summit facility at Rubin, now built and being commissioned, taking data not quite as we speak, but will be this evening. Of course, there'll be lots of other things happening in the Rubin era, but I think this particular observatory is a especially fun context for spending 2 days together thinking about AI and machine learning for science. So that's where I'm coming from. Also recognizing that this audience is of the high variety kind. I imagine there are some people who have heard a bit about Rubin over the last few years, but maybe haven't been following closely. On the other hand, at the other end of the spectrum, we have people here who actually work on Rubin operations, developing the code to analyze the data. So we have the whole spectrum here. So hopefully this talk will be something for everyone. Okay, so imagine if we could image the whole night sky every few nights and do that for 10 years. What could we possibly learn? Well, this was the vision for Rubin, and it's been designed to enable a wide range of science. It's a synoptic survey telescope, to give it from its original name. And so we'll be able to use the data from Rubin to map out the galaxy we live in, try and understand how it formed and evolved. We'll be able to measure the accelerating expansion of the universe to high precision and try and understand what's going on there. We'll use the data to figure out how our solar system formed, taking a census of all the asteroids and Kuiper belt objects and comets and everything else. Maybe see some unusual things, interstellar objects and so on. And we'll also be able to watch the universe as it evolves in real time, so spotting astrophysical transients and variables and seeing how things behave over time, and do that in a way that just hasn't been done to this extent before. So that was the vision. Maybe more than 20 years ago now, we've been working on putting this together. The news in the last year is that after these 2 decades of construction and planning and science analysis development, the observatory is now coming online. So here's a photo taken last northern fall of the night sky through the dome slit, and you can see the Simoniu Survey Telescope ready to go. So I want to give you an update on where we are with the observatory, and then try and give you some pointers as to how to think about the data coming from Rubin. Okay, so here is the Simoniu Survey Telescope, now complete and taking data. It's hard to see the camera in there, but it is there pointing at the primary mirror, all ready to look at the sky. Here's the scene from first photon back in April, where the team in the summit control room saw the first images coming down. And you can see how excited the group are. This is a big deal for many people in their careers. The people who aren't celebrating are the SLAC staff who are worried about the performance of the camera. Okay, so before we got on sky with LSST cam, the biggest digital camera in the world, by the way, we spent some time last northern fall with the commissioning camera, which is a smaller version of the main camera. And so here you can see one of the first on-sky images that we took back in October. And you can see that the commissioning camera has a smaller field of view. It's just the central raft of the LSST cam focal plane in its own structure. But I wanted to show you this just to start us thinking about what it means to be operating the biggest digital camera in the world. So here's a zoom in from that ComCam image where you can start to see we really are observing stars and galaxies. The system does work. This was taken, this image was certainly in the first 10 images taken, so the system worked almost out of the box, which was great. Of course, now we're tuning it up to try and get sharper and sharper images. So you can see with these large format astronomical camera like this, it's all about the digital zoom. So if we go back to thinking about LSST cam, it's 3,200 megapixels. That's what gives it the entry in the Guinness Book of World Records. You'd need 400 TV screens, high-definition TV screens, just to display a single full-frame image. So for astronomy, what this means is we can survey the sky at high speed. For us, thinking about the data products from this amazing instrument, here's one way to think of the zoom power of LSST cam. This is a test image we took at SLAC of a Romanesco broccoli, chosen for its structure on all angular scales. But on the right, you can see what the Earth would look like if you took a picture of it with LSST cam from a plane at 40,000 feet. And so the digital zoom enabled is enough to see a golf ball from that height. So you can see where we're going with this. This machine is going to produce a lot of image data containing a lot of information that we want to use. Okay, so I told you about the telescope. There's the camera arriving at the facility before we put it on the telescope. And the thing to remember about Rubin, its defining characteristic is that it's super fast at surveying the sky. So here's what we plan to do over the next 10 years, starting this coming October. The Legacy Survey of Space and Time, LSST. This will be a 10-year time-lapse movie of the entire southern sky. So we'll be imaging 18,000 square degrees, coming back every few nights on average, taking an image every 40 seconds, do that for 10 years, and build up this enormous image store and associated database. Okay, so let's think about the data products coming from this. All of this imaging needs to be processed. That's done automatically, and measurements of astronomical objects made and catalogued. We talk about database tables as the catalog. And so here's a summary of all the data products. These are made at the US data facility at SLAC. Eventually we'll have 2 other data facilities in the UK and France as well to support it. And the data products will be accessed for the general astronomy user from a science platform hosted in the Google Cloud. So we're thinking about things like terabytes of imaging data taken every night, millions of alerts as transient objects change their brightness in the sky and are captured and processed, and a large catalog to be searched for interesting things. Okay, so what this means in practical terms is that the LSST will give each of its users a big data problem of one kind or another, or maybe several kinds. So we're talking about more data volume, hundreds of petabytes of imaging, more data volume than all previous astronomical observations combined. With those millions of alerts per night, that's a velocity of data that we haven't seen before in astronomy. And this giant database of catalog measurements, sort of hundreds of database columns per object, and many epochs through the life of the survey, we're thinking trillions of measurements of billions of objects. So high variety as well. So, by definition, solving a big data problem means rethinking how you do your data analysis. And I think that's why we're all here, is to think about this particular problem together. So, I think the next 2 days are for sharing and developing ideas for how to solve this big data problem and related big data problems. But as I said, Rubin is a fun context for a couple of days together. So we said data-driven discovery in the title of the conference. What I think that means is this desire to exploit the enormous variety in, for example, the LSST dataset. So that means the information content. Use the information in the data to build more powerful models of astrophysical phenomena. So that's the benefits of the variety. Along the way, we're going to need to cope with the unprecedented volume and velocity of the LSST data without abandoning our principles, please, everybody. So that's what we're going to be thinking about. The next few slides are about how is Rubin going to be helping us, the LSST users, welcome. How is it going to be helping us with the big data problem that the LSST gives us? So I said that there was a science platform in the Google Cloud. Here is how I'm thinking of that RSP account. You can imagine a tiny laptop sitting on top of and connected to an enormous database, and here is a picture of it analyzing the data with the universe in the background. So this was thanks to OpenAI. It cost me 5 credits, I think, so I couldn't make it any better. OpenAI isn't as open as it used to be, but good enough for now. So what this means is that for working with the Rubin data, the way to think about it, I think, is doing the analysis online, not just online in your RSP account in the cloud, but also online in the sense of streaming data up to be worked on, figuring out, producing derived data products, keeping them, and then purging everything else, and then doing it again. So this is how the users are going to be working with the data. And it's useful to have that in mind up front. The tiny laptop part, the storage quota per user at the moment is 20 gigabytes. Okay, so another thing that Rubin is doing to help us get our heads around and solve this big data problem is providing a series of data previews before the first year's survey data release comes out. That first year release, DR2 we call it, is due late 2027, so we have a bit of time. And that time we'll spend analyzing these data previews. So the first one, DP1, is the first one with real data, that is. It's coming out June 30th, right, the end of this month. That's the data from the COMCAM observations that I mentioned earlier. Next April, we plan to put out the DP2 preview, which you can think of as the first science data set. This will be the commissioning observations taken with LSST CAM in the next couple of months. And that will be something like 20% of the first year of LSST scale, so a good step along the way to the first year of the survey. Okay, so the idea is to use DP1 to prepare for DP2, and then use DP2 to prepare for the LSST and get there eventually. And DP1 is nice and small, as I'll show you in a minute. You can read more about the early science plan here. RTN 11 is the thing to remember to search for. And community.lsst.org is sort of like the Stack Overflow for Rubin. It's a lot of information there to search. Okay, even right now, before DP1, we do have DP0. This is a 300 square degree virtual sky survey that the keenest of the LSST users have already been working on for the last couple of years. So that's there as well. It's simulated data made by the LSST Dark Energy Science Collaboration and reprocessed with the same, or close to the same pipelines that we'll use during the survey. And so this is also a very useful data set for getting started. Okay, so how can DP1 help us prepare? I said it was a tiny data set. It's true. It's just 1.5 square degrees, roughly, in Rubin's 6 bands. But one of the fields goes to 10-year LSST depth. Another one goes to 3-year depth. And so it's test data that sort of gives us a feel for what the survey will look like, but on a very small and manageable scale. There's a field that's a nice preview for the 10-year survey depth. There's another one that's good for year 3, as I said. So it's very small, just 0.01% of LSST, but the data products are about the same. The image quality is pretty good, and the data is real. So there's stuff there from the real instrument, from the real night sky. So I think it's a good place to get started on June 30th. Okay, that's my scene setting for you, what we're talking about with Rubin and LSST. Hopefully useful to have in the back of your mind as we listen to all the other thinking about the science and the methods and so on. And all the rest of the talks over the next day and a half are going to inspire you into thinking about this data set, what you might like to do with it yourself or yourselves. And so we're now talking about the run-up to Friday afternoon, which is the main event at this conference, I think. This is the free afternoon that you always wish you had at the end of a conference, right? When you spend the time at the conference in the coffee breaks getting excited, talking to the speakers about what they're doing and starting to bounce ideas off each other and come up with actual projects that you might do together. If you're courageous enough to go and talk to a speaker, maybe you'll end up doing some research with them. And so Friday afternoon is a chance to take those ideas had over coffee time and take the next step, which is to write them down on a napkin and sort of sign your name and whatever and turn it into a project. So that's sort of the default activity on Friday. Turn your coffee time ideas into proto-project plans. It's an opportunity. Another opportunity with the unconference time that we've planned for Friday afternoon is to do anything else you'd like. You don't have to plan a project with a new collaborator. You could try and do something else. And so this is your time to use as you like. Maybe you feel the need to give or receive a tutorial on something. Maybe there's something that's worth some debate that could be set up in a room. It's really time to use however you want. So have this in mind when you're having your coffee breaks and lunch. How are we going to use our Friday afternoon? Maybe we could do this or that or the other, and then the time is open. So for the non-project development ideas, I think we're going to collect them on these bits of sticky paper on your tables. And did we say that we were going to have people stick them to this whiteboard? That would do, wouldn't it? Yes. Okay, we'll fix up that whiteboard so that it's useful. But have in mind coming over here to post some ideas for what you'd like to do on Friday afternoon, and maybe you can we'll get some traction on it. Okay, just to inspire you, one last thing. This is sort of a napkin made in 2001 by Roger Angel, showing the design for the optics of the telescope that has become the Simoniu Survey Telescope at Rubin. It was actually an overhead transparency. That's what they used in those days. But since then, we've all understood that napkins are the right thing to write project ideas on. So that's what we'll try and do on Friday. Okay, thanks very much. 1 to 10 year depth. Yeah. So the 10-year survey is planned to have something like 800 images, frames of the movie taken at each point in the sky. And so we think of the 10-year survey depth in terms of the number of visits that we make to that patch of the sky. And so with ComCam, we took all the data within just 1 month, but we took enough images that it's a series of images that's like the one that we'll have after 10 years. So that's the sense in which it's the same depth and could be thought of as a little place to try out 10-year analysis.